recap of what we talked about yesterday. We did circles yesterday, right? So we said polar functions or polar equations will take on many shapes. The first one we talked about was circles, okay? And we talked about symmetry, which is going to be important to what we're going to do today also. We said the quick test for symmetry. So if you want to go to that slide, I don't remember what slide it was, but the quick test for symmetry is if your function says something like r equals, and there is a cosine somewhere in it, then this would be symmetric to what's formerly known as the x-axis, but we now call the polar axis. So we can fold any of those shapes top to bottom and they should overlap, okay? This is going to become crucial for today. This is going to help us to eliminate a lot of work when we go to graph these things. If it says r equals and somewhere in it there is sine, then it is symmetric to the theta equals pi over 2 line, again formerly known as y-axis. So this one is x-axis. And then today we're going to get to something called a lemniscate, which has an r squared. If it has an r squared, it has, and some of the roses, which we're going to talk about, have pole symmetry, and that means like whatever's happening in the bottom top right is happening in the bottom left, top left, bottom right. It would be symmetric to the origin, okay? But we'll talk about those specific cases when we get to it. Then we talked about our circles, right? We started on the left-hand side of this. So this is circles, okay? And the first thing you're going to do when you get these kinds of equations is figure out which shape it takes on. At the end of today, you'll know 4. Circles, limicons, roses, and lemniscates. There'll be 4 to classify it as. Depending on which one it is, tells you how to move forward from there, okay? But the very first thing you want to do is identify what type it is. And a circle just has r equal to, there can be a number where a is, or it could be 1 and you don't see a number, sine or cosine of theta. It's the most basic one. So if I said something like r equals -5 cosine theta, you want to be able to look at that and say that is a circle. Then you want to be able to look at it and say it has cosine. And if it has cosine, it's symmetric to what? To the x-axis or to the polar axis, right? That means I can fold it top to bottom. So that means it's either going to be on the right or the left. And if you know your circles well enough to understand the positive and negative part of it, if A is positive, then it's going to go to the right. So this is a positive A. And if it's negative, it goes to the left. And so if I know those things, I know -5 cosine is a circle that falls to the left of my y-axis. And I don't have to graph anything other than the coordinate point at 5. That's it. So by understanding your circles especially, it eliminates a crap ton of work. If you don't know that, now I'm plugging in points. Now I can plug in 0, and if I plug in 0, I get -5, so I know it goes to the left. Or I'm plugging in pi over 2, I get 0, so that doesn't really help. So there's going to be points that you can, if you're stuck, you can always plug in. But knowing and understanding these things is going to make it a lot easier. If it's sine, it's above or below. And remember, if it's a positive A, it's above. If it's a negative A, it's below. So if I said graph r equals -7 sine, what does that look like? It's going to be on the y-axis, under my x-axis, right? And how far down would I go? From 0 to 7, I would make my circle, okay? If you understand circles, they are super easy. Questions so far?
Does the radius, the radius matter? Do we have to find the radius?
The radius is technically your diameter is your radius. Okay. Because it would be from 0 to that point. Okay. It's whatever's on the front. That. So you'll put this on if you put this on a polar coordinate grid, you would go out to the 7th ring and I would draw my circle. Yep. All right, so we're going to do this one first, okay? So special polar graphs, the first one, or the second one, we did circles, is called a limicon. Let's go, children, come on. A limicon takes on 4 different shapes. So there's a parent function or a parent shape called a limicon, and then within the limicon there are 4 different kinds of shapes. The first is called an inner loop, and an inner loop literally has an inner loop in it, okay? That inner loop can be on the left of my shape, on the right of my shape, at the top of my shape, or on the bottom. So these can rotate, and we'll talk about what would cause it to rotate. Then there's something called a cardioid, which is a heart shape. So official term is cardioid, okay? Actual shape is a heart shape. It has a little point that comes in at your center or at your pole. The next one is called a dimpled limison, and it looks like a kidney bean. It just comes in a little bit. It's smooth where it comes in. And the last one is called a convex, and it's like somebody threw a ball up against a wall and it got smashed and the side stays flat, okay? And again, these shapes can be where these little sides occur on the left side or the right side, or they can be at the top or the bottom. And that depends on if it's sine or cosine. All of these are cosine shapes because the inner loop happens on the polar axis. All of these have symmetry to the polar axis, right? If I fold them from top to bottom, each one of these, or like a hamburger, each one of these is going to overlap. So these are all cosine. If it was sine, and I was to graph these, now the inner loop is going to happen at the top. So it looks kind of like this. Or the heart will happen at the top, and it will look a little bit like this. Or the flat side happens at the, or the dimpled, sorry, happens at the top, and it looks like this. Or it's flat at the top, and it looks like this. Or they flip upside down. Either happens at the top or it happens at the bottom, okay? And these would all be sine. So the way we spot a limison from the beginning is you will be, God bless you, always adding or subtracting something from your sine or cosine. So with the circle, we only had this part. We only had sine or cosine by itself with a number on the front of it. Now you're adding or subtracting a number to it. That number could be at the front or it could be at the end. So this could say 1 plus cosine theta, or it could say cosine theta plus 2. If it's separated out and you're adding something to it, it makes it a limison. So the first thing we're going to do is say this is a limison. Then we're going to say which of the 4 types it is. And the way we determine that is you find A over B. A is the number by itself. B is the number in front of the trig function. If A over B, and I ignore the positive or negative signs for classification. If A over B is less than 1, then it's an inner loop. If A over B is equal to 1, then it's a heart. If A over B is in between 1 and 2, then it's a dimpled one or the kidney bean shape. And if A over B is greater than or equal to 2, now it's convex. So the way my brain remembers this is I visually try to picture this slide, and I know it starts within an inner loop. And then if I keep pushing that inner loop out, if I took my loop and I pushed it out, it becomes a heart. Push it out further, it becomes dimpled. Push it out further, it becomes flat. So for me, like that's the trick I use to remember which one is which, okay? The smaller the A over B, the inner loop. So smallest inner loop. Next would be heart. Next would be dimpled. Next would be convex, okay? The other thing is like if something equals 1, they're the same thing. So if 2 people love each other the same, you could picture a heart, okay? That makes that shape, something like that. Like stupid cheesy stuff can help you remember this, okay? So first we're going to say it's a limison. Then we're going to say what kind of a limison it is. And the third thing we're going to say is what kind of symmetry does it have. If it's cosine, I know that the loops are going to happen on the x-axis because this is symmetric to the polar axis. I can fold it top to bottom. If it's sine, I know it's got symmetry to the pi over 2, so I know that inner loop or whatever it is going to happen at the top or the bottom. With me so far? Then the next thing to do that's the easiest is find your max point. And your max point, I've written all over this thing, but the max point comes from A plus B. So the maximum radius is going to be A plus B. That's the furthest point out you can get. Then I set my equation equal to that max R, and it will tell you where the rounded part happens. And then I know the inner loop happens opposite it. So it will tell you, is it rounded at the top? That means my inner loop's on the bottom. It will tell you is my rounded on the right? Then it tells me my inner loop's on the left, that kind of thing, okay? So we're going to walk through this from start to finish. But those are some tricks that help you save time on your limisons. Then if you still don't know where to go from there, you're plugging in points. But you want to strategically plug in points. If something is symmetric to the polar axis, if I plug in points above the polar axis, I'm literally just going to flip them. I'm not going to continue to plug in stuff below it. And if I have something that's symmetric to the pi over 2 line, I'll plug in points to the right of my y-axis, and then I'll flip it. So you literally can plug in half the amount of points, okay? Now we're going to get into, I'm going to actually flip-flop this. All right, we're going to go from start to finish on one. So first of all, I know it's a limison because it's adding or subtracting something to it. So this tells me it's a limison. Now I have to figure out what type. So remember, A is the one that's by itself, B is the one attached to it. A is 3, B is 2. So A over B is 3 over 2. Now, which classification is that? Is that less than 1? Is it equal to 1? Is it in between 1 and 2? Or is it greater than? In between. If it's in between, which type of limison is this? Dimpled. A is the one that's by itself, what you're adding to it, and B is the one that's attached to it. Now, what kind of symmetry does it have? It's to the polar axis or the x-axis. That tells me that the dimple is either going to happen on the left-hand side like this, or it's going to happen on the right-hand side like this, okay? So already I know that information. Next, I'm going to find my max point. My max comes from adding A and B. Again, we ignored the signs on A and B when we add them. So A plus B is what? 5. That tells you that the furthest point out, the biggest R you would get is 5. Now I'm going to find out where that happens by setting my equation equal to 5. So 5 equals 3 plus 2 cosine theta. Now I'm going to subtract the 3. 2 equals 2 cosine theta. I'm going to divide by 2. 1 equals cosine theta. And then I'm going to say, where is cosine 1? And you're going to tell me 0. So 5, 0 is a polar coordinate that is on this graph. So I set it equal to R. I solved, and I got cosine of theta equals 1, and cosine is 1 at 0, right? So that tells me 5, 0 is a coordinate point. So I'm going to go 1, 2, 3, 4, 5. And I know that's the rounded part of this shape. So it's going to do something like this. You with me so far?
Wait, how do you know which part's rounded?
When you find your max point, that's the biggest point it can be. That's the furthest out. That will be the rounded edge. So we found it was at 0. It will either be at 0, pi over 2, pi, or 3 pi over 2. And then that's where you know to make it rounded. And then opposite the rounded is going to be the other shape, either the loop or the heart or the dimpled or the flat. Okay? All right, so now I know all this information. I know where the max point is. I know that it's symmetric to the polar axis. And I know it has a dimple. I'm still going to plug in points. So you can't avoid plugging in points when it comes to a limison. Okay? But I can really only plug in a few points because I overall know the general shape of my curve. I'm going to plug in something from my first quadrant, and I'm going to pick the middle. I'm going to plug in pi over 4. But you could have plugged in pi over 6, pi over 4, or pi over 3. It doesn't matter. Pick one in there, okay? So the curved part, just 1 point's enough. But then on this side, I need it to be a little bit more specific. I need to know what's happening at that dimple. So I'm going to plug in 3 points from the quadrant that has that shape. I'm going to plug in 2 pi over 3, I'm going to plug in 5 pi over 6, and I'm going to plug in pi. So wherever the rounded curve happens, pick 1 point from that quadrant. But then where the other weird shape happens, pick 3. And by plug in, I mean literally I'm going to plug in each of those. So I'm going to make theta 2 pi over 3. So I get 3 plus 2 cosine 2 pi over 3. 3 plus 2. What's the cosine at 2 pi over 3? Negative 1/2. So I get 3 minus 1, which is 2. So I have a coordinate point at 2 pi over 3. I'm going to come over here. I'm going to plot it. So I'm erasing our approximation, and I'm going to make this more accurate. We know this is a point. Now we know 2 pi over 3 is a point, which is there. Then I'm going to plug in 5 pi over 6. I get 3 plus 2 cosine 5 pi over 6. 3 plus 2, what's cosine at 5 pi over 6? Negative root 3 over 2. So the 2's cancel, and I get 3 minus root 3. What did we say we were going to make root 3? 1.7. And I get 1.3 as the radius. So now I have 1.3, comma, 5 pi over 6. So I go to 5.6 and I make it 1.3. And then I go to pi. If theta equals pi, then I get 3 plus 2 cosine pi. What's the cosine of pi? Negative 1, good. And 3 minus 2 is 1. So 1 pi is the last point I'm going to get so that I can then duplicate this. Sure. It's an interesting decision, but you go right ahead. With me so far? Okay, so now what's true about my... Oh, I erased the one that was at pi over 4, right? We plugged in pi over 4? No, we didn't plug in pi over 4 yet. I said I was going to plug in pi over 4. Theta equals pi over 4. And I get 3 plus 2 cosine pi over 4. What's the cosine at pi over 4? Root 2 over 2. And root 2, we're going to approximate to be 1.4. So I get 4.4. One, two, three, 4. So I know this rounded shape is going to come all the way around, and then it has to dimple. So it's going to come out and in. I lost this part. There. Okay. And then everything that happens above also happens below, which means if I have a coordinate point at pi over 4, that is 4.4, then at 7 pi over 4, I'm going to have the same coordinate point. Whatever's above reflects down below. If I have a point at 2 pi over 3, that was 2, then at 4 pi over 3, I would also have a point at 2. If I have a point, this is 2 here. If I have a point at 5 pi over 6, that's 1.3. Then at 7 pi over 6, I'm also going to have a point that's 1.3. And if I have a point at, oh no, and then the axis is the same thing. So there goes my shape. This one actually probably dips a little bit further down. That looks sort of like a kidney bean. Yep. They're weird. Wait till we get to a loop, okay? Yeah. So every one I had at the top, so the one at pi over 2 pi over 3, this one, I duplicated down here. And then at 5 pi over 6, I had one. So I duplicated it at 7 pi over 6. And then there's one on the x-axis, so that one, it wouldn't matter. It would stay the same because you're literally on the x-axis. Yeah.
How did you find out that it was symmetric to the polar?
Because it's got cosine in it.
Oh.
Yep. So the other thing I could have done, like I could have plugged in pi over 2 to see how high it's going to go or how low it's going to go there too. You could do that. Like there's no limit to how many points you can plug in. It just requires extra time. Yeah.
Why'd you plug in pi over 4? Could you have done like 11 pi over 6?
So I wanted something in my first quadrant. Yeah, you could have plugged in the fourth quadrant and then duplicated it up. to me, the first quadrant ones we're just more familiar with. So if it's picking between 1 and 4, I would pick 1 and reflect it down to 4, but it doesn't matter. Yeah. The other thing is another trick. So we talked about where the max occurs. The min would be is A minus B, and that occurs opposite your max. So if my max is here at 0, then my min is going to be here at pi. If my max was at pi over 2, then my min would be at 3 pi over 2. So they're always opposite each other, okay? Your minimum can be negative, so keep that in mind. If your minimum is negative, that causes the inner loop. That means it's going to go up. All right, so these are one of those things that's totally going to take practice, okay? Because the more you practice it, the more strategies come into play. If you know nothing about your shape, the punishment is you have to plug in a crap ton of points. The more you know about the shape, the easier it will be. If you forget to do with what to do with the max, then literally you would just keep plugging in points and you'd find the max. Like if I plug in 0, I'd find my max. You would just keep finding points, and then you'd have to I would always duplicate, otherwise you're going to plug in a lot. You want to use symmetry always, but even if you forget your symmetry, you could use these points. On your test, if you get a limison, which you probably will, it's going to ask you, if it's a limison, classify what type. So you'd have to know if it's the loop, the heart, the dimpled, or the convex. Then it's going to ask you for your symmetry, which would be the polar or the pi over 2. And then from there, it's going to say graph it. And you get to choose. Do you use the tricks that we talk about, or do you blindly plug in points and graph it? Okay? But that's going to take practice. Questions on the limisons. We're going to graph them all eventually, all the different types. But the strategy is there. Okay. Then we get to roses, okay? Roses, to be honest, they're pretty. They have petals, okay? They're called roses because each of those little things are called a petal. And there are 2 different types of roses, okay? Ones that have an even number of petals and ones that have an odd number of petals. And the way you determine that is the number that is next to your theta. So notice what changes in an equation for a rose is there is something next to theta. That has not existed in any of the other ones we've seen, okay? If there's a number next to theta, it's a rose. If that number is odd, then that is the number of petals. So if it said 3 theta, there are 3 petals. If it says 5 theta, there are 5 petals. If that number is even, then we double it to get the number of petals. So if it said 2 theta, then there are 4 petals. If it says 4 theta, there are 8 petals. There cannot be 2 petals. That's called a lemniscate. It's completely different, okay? So the minimum amount of petals you can get is 3. The length of each petal comes from A, the number on the front. So kind of like what we did with the circle, the number on the front is going to tell you how far out to go. That's your petal length. Then you're still going to use symmetry. If it's got cosine in it, it's symmetric to the polar axis. So all of these would be able to fold top to bottom. If it's got sine in it, then it's symmetric to the pi over 2 line. So these would all be able to fold sideways. If it has got an even number, it's going to have both. So if it's got an even number, it's going to have polar axis and pi over 2, and that means it's got axis symmetry to the pole too. So an even number of petals have all 3 types of symmetry. So you start the same way. Identify what it is. Then once you know it's a rose, you're going to figure out the number of petals. Then you're going to say the length of each petal. Then you're going to say the symmetry. And then the first thing I do after that for a rose is I set my equation equal to the petal length. and I find one petal. And then I have to use symmetry or plug in additional points to find the rest. So again, first comes, okay, this is a rose. How many petals does it have? What's the length of the petals? What kind of symmetry? And then find the first petal by setting it equal to it. We're going to go to the petal and then we'll come back. I mean, we'll go to the rose and then we'll come back. So example 3. Analyze the graph of r equals 2 cosine 2 theta. Identify the type of curve, the symmetry, the zeros, and then verify using a graphing calculator. So we'll check this at the end. So first of all, I know this is a rose, right? Because there's something next to theta. So this is a rose. How many petals does this rose have? 4 petals. What type of symmetry does this rose have? All 3. What's the length of each petal? 2. Good. The number on the front, not this 2, this 2. That determines that. So the first thing I'm going to do is say, okay, if the petal length is 2, let's find where one of those petals is. So set it equal to the petal length. I would divide both sides by 2. 1 equals cosine 2 theta. Where's cosine 1? 0. But this is a multiple angle. You remember these? So it happens at 0. But I set, instead of it just being equals theta, it is 2 theta. With 0, it doesn't matter. But if that said pi, it would matter, right? If I divide both sides by 2, I get theta equals 0. So that tells me that one of my petals is at 0. So my petal goes like this. Now, if it has all 4 types of symmetry, where are the other petals? Across from it, because it has symmetry to the pi over 2 axis. I still need 2 more petals. Where could they go where it would reflect over? At the top and at the bottom. That's it. If you know what you're doing. If you don't, you're going to sit here all day and plug in points, right? And if you were unsure about that, then I could plug in a point at pi over 2. So I would say 2 cosine 2 pi over 2. It's really hard to read, right? 2 cosine 2 pi over 2. Now these cancel and I get 2 cosine of pi. What's the cosine at pi? -1. So I get at pi over 2, my radius is -2. So at pi over 2, that's at the top. Which direction would I go? If it was -2 for my radius, I'd go opposite, which would put it here. And then I would know it's reflected above. Or again, I could check by plugging in 3 pi over 2. And if I plug in 3 pi over 2, I'm going to get -2. And it's going to tell me put it at the top. Okay. If you don't, like if it's not as odd, so sometimes the odd ones aren't as easy because they don't have all the symmetry. You're going to use either polar axis symmetry or pi over 2 and you'll reflect it. You might have to plug in a couple of points with a rose. It's okay. Okay. Some of these are going to require, you get lucky on a rose, you don't have to plug in any points. You just have to set it equal to your petal length. But if you have to plug in points, maybe you're plugging 1 point in from the first quadrant so that you can reflect it in one way or the other. Yeah.
Do all roses have very symmetry?
No, the even ones.
Oh, okay.
So only the even ones. If it's odd, it will have one kind of symmetry. It could be to the pi over 2 line, or it could be to the polar axis. So like if you found, let's say it had symmetry to the let's say it was sine. I don't remember if this is it, but let's say it's this, right? So let's say I found that this had that was where one of my petals was. I know there has to be 3, and I know it has to be symmetric to this line, which means something has to happen here and something has to happen there because it has to be reflected. So I would have plugged in a point from the fourth quadrant or the third quadrant, and I would have reflected it over to the other way. All right, so again, you have to first be, so you want to check your mode, you've got to be in both polar and radian, okay? Then when I go to my y equals, it's going to give you an r instead of a y. I am recording. I know it's glitchy, but I am. And I'm going to type in, I'm on example 3, so I'm going to type in 2 cosine 2. When you hit the variable button this time, it gives you theta. I'm going to hit enter. And then I'm going to hit graph. Oh, I'm so zoomed in. Let me adjust my zoom. Oh, I didn't mean to do that.
Does the 2 go into the parentheses?
The 2 goes into the parentheses. Yep. Okay. There's your rows. Yep. And it will graph it. If you pay attention, it's going to graph it in the order that you would get those angles. So it would start at 0 and it would go to 2 pi. The last kind is the limnescate. Okay? And a limnescate looks like an infinity symbol. It looks like a rose with 2 petals. Okay? It is the most unique formula because what do you notice about r? It's squared. It's the only one that has an r squared. So the limnescate has an r squared, okay? Because it has an r squared, it will have pole axis symmetry. Because if I plugged in a negative r, it would always go back to positive r. So these are always symmetric to the pole, which means what's happening in the top right is happening in the bottom left, okay? If it is cosine and a limnescate, now it's got symmetry to all 3. If it's sine and a limnescate, it's pole and pi over 2. If it's cosine, it's pole and pi, which would also be all 3. All 3. And for these, I take the exact same approach. The a, this time, is squared in the formula. So the first thing you're going to do is square root the number on the front. And then I'm going to set it equal to it. And then I'm going to find where it is. And then I'm literally going to duplicate it wherever it's symmetric. Okay? So you only have to find one petal in a limnescate because they're always going to have some sort of symmetry. All right, last one. So I know it's a limnescate because it's got an r squared. Oh, yay. There it goes. What is my a? Good. Because I square root what's here. That's your a squared. What kind of symmetry does it have? The pole and pi over 2. Good. Because it's got sine. Now I'm going to find where one of those loops are. I'm going to set it equal to 3. So I plug 3 in here. 3 squared equals 9 sine 2 theta. 9 equals 9 sine 2 theta. 1 equals sine 2 theta. And then where is sine 1? Where's your y1? Pi over 2. So pi over 2 equals 2 theta. And then I have to divide by 2 at the end or multiply by half. And I get theta equals pi over 4. Let's just finish this one. So then I would find my pi over 4. I would go out to 3. And I would draw my one petal. And then I go exactly opposite it. And I draw the other one. So limnescates, you only have to find that one. And then you know it goes opposite it. It makes that infinity symbol. You got to remember, I would say the biggest mistake with limnescates is not square rooting what's on the front of the sign. You have to square root that to get the A. But then after that, plug that back in for R, solve, and find where your petal is. Questions? So 4 different types of classification. There's a lot in this section, okay? Your homework is a PDF because you have to hand draw this stuff. Some of them are matching, so it's not so bad. But anything that is just like graph this, you got to make sure you do the classifications that you're supposed to do. What kind is it? If it's a limnoscate, within the limnoscate, which of the 4 kinds? If it's a rose, how many petals? If it's a limnoscate, what kind of, and well, for all of them, what kind of symmetry do you have? Okay. For the rose and the limnoscate, what's the length of the petal? For the limnason, I would say you want to find the max and the min. Those kinds of things are going to help you. And then when in doubt, you've got to graph it all the way through. So these can be graphed on your handheld. Okay, if you want to get your graphing utility out, we're going to check 2 of them because I'll show you how to do both. You will not have a graphing utility on your, no. But I would say like if you're stuck and frustrated and you're trying to do homework, this would be a good way to help you. Or you want to cheat and work your way backwards. Mm-hmm. I get it. Sometimes you get stuck. If it's r squared equals this, and I need to make it r, what do I have to do? You have to square root, and when you square root, you have to remember to do what? Plus and minus, which means you're typing in 2 equations for this guy. You're typing in square root of 9 sine 2 theta, and then you're typing in negative square root of 9 sine 2 theta. You don't have to solve what's underneath it. You just have to type it in. So second square root 9 sine 2 theta and negative square root 9 sine 2 theta. Enter. So I typed it in as 2 separate ones. Again, one with a positive at the front, one with a negative at the front. And the negative has to be this negative. You can't use the minus sign. And then I hit graph, and I got my lemniscate.
But it gives you the same thing, no? Like on top of each other?
What?
Like when you put plus or minus.
Plus or minus. So the plus is giving you this guy, and the minus is giving you that guy.
Oh, okay.
Yeah, you would have to have both in order for it. So if I took off the, I only get half. Hang on.
Oh, okay.
If you take off the negative, you only get the one in the top right corner, and then in the first quadrant. You need both to make it work.